Well, we're going to switch the order if it's okay, because I'm Michael Green. I'm going to start, and then Andrew's going to go next, because our two talks kind of synchronize with each other. And Andrew and I have prepared about 7 hours worth of speaking that we're going to collapse into 30 minutes, and I'm not even kidding. So I'm going to move fairly quickly through this presentation, which I call my part Evolution Revolution, which is really about the future of where we hope to see a lot of wood buildings going, especially in urban environments. My firm is in Vancouver, Canada. And we're a small firm, we're about 30 people, 35 people, about 8 years old, and we've been building buildings like this in wood all over the world. We build in different scales, little tiny projects like this one, big airports, international airports, Moscow, Chicago, in this case Ottawa, the capital of Canada. We always use wood. We always try to use wood in our structures as well as in other aspects of the projects. But really, these buildings are not what I'm going to talk about. I'm going to talk about a research project we're doing, spurred by some of the work that Andrew's doing, and I'm going to talk in the broad principles of why we've been doing it, and then Andrew's going to dive into more and more detail in his presentation. So I usually start my talks with this quote that I like. It's, I put my money on solar energy. I hope that we don't have to wait for oil and coal to run out before we tackle that. That's a quote by Thomas Edison, and that quote came 80 years ago. And of course, all of us that are involved in pretty much anything in the world right now, we're sensitive to the fact that we are all working hard to address climate change issues. We're trying to address green energy solutions. And in the architecture industry, this is a huge part of what we all are involved in worldwide, in trying to improve the character of our work with respect to the environment and climate. But what we like to say and recognize, and everybody here of course recognizes, is that certainly within architecture, the only significant building material we use that's already grown by the sun, that's already harnessing solar energy, is wood. And that's a fundamental that unfortunately has not reached the breadth of our industry that we're working on. And ultimately, man cannot compete with photosynthesis today in architecture, and that's kind of the essence of what brings us here. So this little next part is what we call evolution, which is just how we, for instance in Canada, where we have this great tradition of building in wood and log cabins are kind of our beginning, how we moved in architecture over the last century from log cabins to Burj Dubai and these huge buildings around the world. And of course the answer is the Industrial Revolution. Really triggered by things like Gustav Eiffel's decision to start pushing the boundaries of what new materials were possible. And with the Eiffel Tower, when he set out to sort of push the boundaries of what wrought iron could do, it became this sort of iconic message of what was possible. His desire to stretch the imaginations of what was possible is what was important about this building. From this time, from these kinds of stretches of what was possible, we of course created the skylines that we're all used to today in concrete and steel. Because really over the last century, everyone that was a thought leader in architecture and engineering were really focused on the limits and the potential of concrete and steel. And wood, unfortunately, to some degree, certainly in a lot of developing countries developed countries became regional and residential. And innovation ultimately slowed, so such that, you know, a lot of the housing that we see built today in Canada and the United States, for instance, is built the exact same way it was built 150 years ago before the Industrial Revolution. And there's a funny paradox. Over the last century, what's happened, this little diagram is about building codes and what we're allowed to do. And BCBC is actually the building code that I work with in Western Canada. We were only allowed to build 4-story tall wood buildings until 2008. And then a lot of people in Western Canada worked on pushing the boundaries of what was allowed. And we were allowed all of a sudden with our new building code to push up to 6-story tall wood buildings. And of course, these are lightweight wood frame buildings. And that was a pretty exciting thing, but by the time our code had already changed in Canada, in Western Canada, to 6 stories, Andrew had already built a project that was 9 stories tall in London that he's going to talk in more detail about. So our building codes weren't even keeping up with what was already happening elsewhere in the world. And although Andrew was pushing the boundaries of what's imaginable today, we believe that these code limitations, ironically, have created these contexts that stifle our ability to innovate within wood and within architecture. So when the 6-story building code changed and was announced, I was actually riding my bike across Japan, and I got an email from my office, and I read it and said, "Isn't this great?" And I said, "Sure, it's great that we can now build 6 stories, but the problem is I'd already walked out of a building that was 19 stories tall." And what's really profound is that building was built 1,400 years ago in a high earthquake zone, wet climate, similar to Vancouver, and is still standing today. So the problem is we've created over the last century ways to limit our imagination that can't even keep up with what we were doing 1400 years ago, and obviously this has to change quickly around the world. So that's a bit of context of code. So why change now? And obviously the answer is climate change. Steel and concrete have been incredible buildings, materials in the urban environment, and there's no reason to challenge them until we start factoring climate change. If you know the statistic, concrete represents roughly 5 to, some will say, up to 8% of world carbon dioxide. Greenhouse gas emissions comes from the manufacture, transportation, and chemical process of manufacturing concrete. Obviously, we need to sort of revisit that if we're actually going to tackle the scale of the problem within buildings. And buildings represent, depending where you are on Earth, the United States, they represent roughly 50% of the footprint of greenhouse gases, and 50% of energy use are related to the building industry in some way. So it's a profound part of the problem and the solution. So really, when it comes to carbon and energy, the two major conversations that we're having, really we know, and I think everybody here recognizes that wood is always our best choice if it's sourced from sustainable forest practices, and what we believe if we design with more rapidly renewable wood solutions. And that's part of the reason that we're here and why I'm here, is that on the architectural end, we're starting to design with products. I'm going to talk about the products that are available today, and we are hoping that scientists, researchers within the wood spectrum are starting to explore ideas that allow us to use more rapidly renewable tree species and engineered wood products that make a more sustainable solution. I use this slide, this is easy in this audience, but I use this slide to communicate with lay people about just the importance that 1 cubic meter effectively sequesters away a ton of carbon dioxide, or current research done at FP Innovations in Vancouver is actually showing up to 1.6 tons. So here's what we're really up to, okay? We're designing currently in my practice and the research papers that we're working on, buildings that are now 30 stories tall in wood. It's a very new way of building, and we believe this is the future, and I'm going to show you what that looks like. 30 stories tall is a little bit like that conversation of the Eiffel Tower. It's sort of bending the rules of what people think is possible, and really it's not because we want to build 30-story tall wood buildings tomorrow, although I'd kind of like to do that. We're not trying to do that tomorrow. What we're trying to do is actually show that from an engineering and a technical point of view, we can do that. And when we start to expand people's minds that 30 stories is possible, all of a sudden obviously it becomes a lot easier to be talking about 10, 12, 15 stories. And so why does that actually matter? Well, in part because of the climate change and the alternative of using concrete, but really it's possible because these new wood products are changing the scale of what we can do. And what generally the terminology that we use, and I'm not sure what is used elsewhere in the world, but is mass timber. Mass timber technology is what's changing everything about the way we build. And certainly in North America, this is still a very new conversation. Really around the world it is. But these mass timber products that many of you are familiar with already exist and have existed for some time now. CLT, cross-laminated timber. Andrew's presentation is going to talk a lot more about that one. These incredibly large-scale, massive pieces of, that's fantastic, there's a bird in here. Large pieces of wood that are engineered by gluing them together. Laminated strand lumber, LSL, is the product that we're working with a lot right now in Vancouver, and LVL. These huge scale panels currently are cut up into small pieces and used as beams in North America and in Europe. But by keeping them in their original format, in their large scale sheets, it actually allows us to reimagine the scale of the buildings we can build, and that's what's unlocked the problem. So in our case, there are many systems and ways that you're going to be able to build this way in the future, and we're out there trying to encourage architects and engineers to generate new ideas like this. The one that we've generated is called FFTT. And FFTT actually stands for, people want to think that it's a jargon, a sort of very sophisticated acronym for something important, but it actually stands for finding the forest through the trees, which is really what we believe architecture needs to do. We need to step back away from solving green building solutions, environmental solutions, by putting green roofs on our buildings, or just thinking that we change the glass and we've solved the problem of the Earth. These are good things, but we need to look at systemic change. And this kind of building structure, this new way of building, we believe will be part of systemic change that we need. So FFTT is a new alternative to steel and concrete buildings. And why? There's a whole host of reasons. I've talked about climate, but the other reason why that's really important is that over the next 20 years, the UN Habitat statistic is that 3 billion people in the world, or roughly 40% of the world, will need a new affordable home in 20 years. The quantity of building that we ultimately have to achieve in the next 20 years just to meet human need is so great that if we do it using today's technology, if we do it using concrete, as we will in most of the world, to deal with large-scale buildings, we effectively will solve the human need of shelter and in turn exacerbate the issue of climate change. So we can't accept that model. We have to find a new way, and we have to do it by changing codes, changing materials that are available to us, and changing the techniques that we build. The other really important issue is that a lot of architects around the world are going to show you examples and talk to examples that are more suburban scale examples, single houses. What we're interested in is in this new statistic, these statistics that we all are getting used to, that 70% of the world will be urban. Today, 50% of the world is urban. Woo, let's go. So a couple really quick stats. This is hard to absorb in a short amount of time. I'm under the gun. 400 million people in China are going to move by 2030, in the next 20 years, into cities. That means, again, we can't solve the scale of the problem. It's 215 million that are going to move in India into cities. What that means is, again, we can't solve the problem with single-family residential style solutions. We need to solve it with big urban buildings, and we need an alternative. So that's the equivalent in China of building 10 New York cities over the next 20 years, or roughly the footprint, the area of Switzerland. It's an amazing thing to get your head around. So the revolution part of the presentation, I'll go really fast, is around how we actually are doing this. Again, it's called FFTT in our case. It's a very simple system of building. It's really like steel frame construction, but done in wood. It does use a little steel. We've engineered, again, to 30 stories at a conceptual level with some engineers in Vancouver. We're getting peer reviewed right now for that work. The idea is the system is simple to build, it's cost effective to build, and it's adaptable to many different architectural styles and characters like steel and concrete have been, and it works in high seismic regions like Vancouver. So we're not quite California for high seismic, but some of the strictest seismic codes in the world. We did our study, I'll be able to spin through this quickly, comparing concrete buildings, which is the way we build in Vancouver today, to the future of FFTT. We looked at it in all kinds of different avenues: technical performance, cost performance, environmental performance. And what we found, which was very important, is that this approach to building is adaptable in the public sector, adaptable in the private sector. It allows us to build residential buildings, it allows us to build office buildings, again, all to that 30-story mark. And we actually think we can go higher than 30. We're just, truthfully, we're scaring the Canadian government like no tomorrow by talking about 30, so we're going a little bit at a time, and it's baby steps, but it's important. We've gone through these huge exercises of looking at all the technical resolution of how that is, and we decided, well, let's put together a picture of what it would feel like to live in a skyscraper in Vancouver with our beautiful view of the Lionsgate Bridge looking through all this wood. And we did it in 2 different techniques that we have with solid wood. And so just quickly, footprint-wise, why this matters on the carbon footprint on the right there is the important stat. If we built this a 12-story building in concrete, we'd be producing roughly 400 kilograms, 400 tons of carbon. And I'm done. Hold on 1 minute. And the last slide here that's really important is that we've been able to show that it's actually cost competitive. And that's what matters. We're now expanding that work across North America and future to Europe. We've been able to show that it competes with concrete, and that'll make it real and happen.
Thank you. Very well.